Hello, everyone, and welcome to another wonderful day of chemistry. So, today we're going to be finishing up chapter one by talking about unit analysis. So, unit analysis is actually what I think is one of the most important topics in chemistry. And to be fair, it extends way beyond chemistry. You can solve so many mathematical problems if all you do is show the units. And as a result, I'm going to be fairly picky this semester about looking at the units of all your mathematical problems. And one of the reasons why is when I was a chemistry student, I was in an upper level chemistry class called PChem. And realized that there were so many problems, I couldn't remember all of the equations I needed to solve them. But what I could do is if I followed the units and was able to track the units through the problem, I could usually get the problem right. And that's kind of the power of the units. If you're really careful with labeling your units and you follow them right, it will often help you solve problems that you couldn't do otherwise. So units are huge. And again, you can solve so many problems if you just follow the units around. And one of the useful things to keep in mind when you're starting this follow the units approach is by realizing that most conversion factors that we're going to use in chemistry, such as conversions in between units, can just be treated as fractions that can switch units in a problem. So for example, if I'm going in between inches and centimeters, I can either treat it as a fraction of 1 inch contains 2.54 centimeters, or 2.54 centimeters contains 1 inch. And what we can then do is use these ratios in something called dimensional analysis in order to convert units. Dimensional analysis is often also described as railroad tracks, and it is the most single useful skill that you will learn this semester. So the general idea is you'll start with whatever unit you were given. Say I tell you something is 12 inches. And then you write down the unit that you're aiming for, say centimeters. So then if I've got inches up here, I need to have inches on the bottom. So that means that I'm going to need this ratio so that my inches cancel out. It's going to be inches over inches. And then what results is the ending unit, centimeters. So if I've got 9 inches, I use this ratio. I've got 9 inches divided by 1 inches, which is just going to be 9 with no units attached, times 2.54 centimeters. I do this, and I'm going to get a number of 22.86 centimeters. Then we use our knowledge of sig figs and realize that I've got 2 sig figs here, 3 here. 1 has infinite number of sig figs because it is a whole number. And as a result, I'm going to have 2 sig figs on my products. It's 23 centimeters. So with just a little bit of sig fig knowledge and a little bit of unit knowledge, we can solve the problem. However, most problems aren't going to be quite so simple as this. They often involve needing to couple together multiple unit conversions. So I have one starting unit and I have another desired unit that may not be directly correlated. So I may need to do unit conversion multiple times along the way. So let's say I want to go from feet into centimeters. Well, I know how to go from inches into centimeters, so that could work, but that means that I need to have a way to go from feet into inches. And we can do the same thing. We start with 1 foot, and I convert this to inches. So there's 12 inches in a foot, mind noting that these are both whole number conversions, and I'm starting with a whole number 1 foot. And then I use my inches to centimeter conversion. Again, watching out that the units cancel out. Feet cancel out, inches cancel out, and the only unit left behind is centimeters. So this gives me an answer of 30.48 centimeters, which rounds to 30.5 because the only number here that contains sig figs is, again, that centimeters with 3 sig figs. So this works for fairly shorter conversions. However, we often need to perform longer unit conversions. So it's useful to have a more general approach. However, it follows most of these same rules. You're always going to want to start down by writing the amount, the given amount and unit. Then you're going to want to write down what you want to find and what its associated unit is. This often means that you're going to then you're going to need to write down all of the conversion factors that will get you along the way. So these are often can be done as equivalent statements, which can then be turned into conversion factors. So again, we're going to want to always put the starting unit on the bottom. And then this is where it gets a little bit tricky. You often want to do the solution map. Try putting in multiple conversion factors, make sure that everything cancels out, and so you only have the desired unit at the end. Then we're going to check that all of the units cancel and multiply terms across the top and divide by all the terms on the bottom. Then we can check out for sig figs, round, and report. Then always make sure to do this. Check your work. I always like to make sure that it goes past the smell test, that nothing seems a little fishy. This is a good way to note that that things might be wrong. And then again, double check to make sure that your units are correct. And you can use this to solve any number of problems. And one of my personal favorites is the good old Archimedes Principle. So this was the idea that you can go ahead and use unit analysis to find things like the density of a gold crown. And what you can do is figure out the density of this gold crown by knowing the weight of a gold crown. So let's take an example, gold leaf Greek crown, because this is what Archimedes worked. And he said that you should be able to figure out the density by figuring out how much water it displaces. So let's say this crown displaces 13 milliliters of water. We want to use this to figure out the density. So this means I'm going to want to have a ratio, and this makes this problem a little weird, of mass to volume. And that my ending units should be, if I'm looking at the density of a solid object, I should aim for grams per centimeters cubed. So now we need to figure out a way to go from this ratio to this ratio. Now, one of the big things that I'm a fan of is start with the units, worry about the numbers later. It's easy, really easy to get mixed up with the numbers. Make sure you have your solution mapped first. So first thing I often want to do is let's check out the top units, kilograms to grams. Well, I can do this. I can go from simple unit conversions of kilograms to grams. That just leaves me of milliliters to centimeters cubed. Well, I can do that too, but here I have to watch out. This is the reason I like to be very precise with units, because I'm displacing 13 milliliters of water. I'm looking for cubic centimeters of gold. Well, here it comes in handy that we know that a cubic centimeter of water should be the same as a cubic centimeter of gold. So these units should convert easily in this case. You're not always so lucky. So the next thing we do is we put in all of the unit conversions. So there's 1,000 grams of gold per kilogram, and 1 cubic centimeter is the same thing as 1 milliliter. And as I said, the cubic centimeters of the two substances are equal. This goes ahead and gives us a final answer of about 19.31 grams per cubic centimeter. But we're not done yet. Now we have to watch out for sig figs. So all my conversion factors are all whole number conversions, so I don't have to worry about them. But now I have to worry about my starting numbers. The mass of gold has 3 sig figs, but the volume of water is 2. So my final answer has 2 sig figs. So these are some simple cases, but this general approach will take you a long way. And again, unit analysis is one of the most powerful tools in science. And it will help you in so many different ways and in so many different fields, no matter where you go. So I find this is one of the most important skills you'll develop this semester. So that brings us to the end of the introduction to chemistry. Next time, we're going to dive into the structure and nature of matter. Deep stuff. Till then, take care.